A unique compound that known measurement can then be used to determine the same analyte's mass in the mixture, as long as the relative quantities of the other constituents are known. So there are different the four main types of methods of this analysis, like precipitation, volatilization, electroanalytical or thermogravimetric analysis are involved. So in gravimetric analysis, the amount of analyte is calculated by measuring the weight, by measuring the mass of a pure substance containing targeted analyte. In gravimetric analysis, we mainly concern with the uh, formation of precipitates. These precipitates are insoluble in the mother liquor. In next slides, we will talk about the mother liquor and the concentration parameters that we have to look into that we have to take in our concentration for the completion of the this analysis. In order to perform gravimetric analysis, we will have to take the following steps that are shown in this slide. These steps are taken in consideration for the successful completion of gravimetric analysis. These steps include preparation of a solution and followed by the precipitation, digestion of the precipitates, and how we will isolate these precipitate from the mother liquor involving the filtration process, then washing of the precipitates, drying, weighing of the precipitates, and then finally calculation involved in this gravimetric analysis to calculate the exact concentration of the target analyte. So we'll start with the preparation of the solution. Actually, solution is a homogeneous mixture of two or more substances. When we add some amount of solute into a solvent, then a solution will be formed. So solute is always a small quantity in comparison to the solvent, and solvent and solute must be uh, uh, compatible to each other. Just dissolve like dissolve. If we are choosing a polar solution, then the solute would be a polar, and if we are going to select a non-polar solute, then we will also select a non-polar solvent to get homogeneous mixture. So this homogeneous mixture, a solute is a substance dissolved in another substance known as solvent. So one is solute, another is solvent. The mixing process of a solution, when we mix these solute and solvent, then a homogeneous mixture is formed, and this solution must have some characteristic features, like a homogeneous mixture should contain two or more substance in it, number one. Number two, the particles of solute in a homogeneous mixture cannot be observed by a naked eye. They are solubilized in the solvent, so they cannot be seen by the naked eye. And then the solution does not allow a beam of light to scatter. A solution is a form that must be stable. A solution must be stable after formation of homogeneous mixture. The solute from the solution cannot be separated, and this separation involves the filtration process or any mechanical way. The solute, once the solution has been formed, that solute cannot be isolated or separated from the solution, and these solutions must be composed of only one phase. So these are some properties of a true solution, and then we'll talk about the precipitation. precipitation actually is a formation of a solid particle from the solution, and when we add some precipitating agent which is known as precipitant, then these precipitating agent will react with the solution, with the analyte in the solution, and a solid material will be formed. uh, Without sufficient force of gravity, it is unable to settle down the precipitate which are formed as a result of a reaction between solution and the precipitating agent. So uh, after sedimentation, the precipitate may be uh, known as a pellet, and precipitation can be used as a medium. The precipitation uh, free liquid remaining above the solid is called supernatant or supernate. And the next step is uh, the digestion of the precipitate. When the first step is a preparation of solution, and the second step is addition of precipitating agent to the solution. After the addition of precipitating agent, some precipitates will be formed, and these precipitate will be digested in order to get a bigger and a cleaner crystals of the precipitates. Uh, after after having these crystals of the precipitates, these precipitates must be separated from the mother liquor. Mother liquor is a solution in which the precipitates are formed. So these precipitates must be separated from the mother liquor by using a filtration process. And after filtration process, these precipitates will be washed with the distilled water or deionized water, depending upon the protocol of the analysis. And once the precipitates are washed, then these precipitates will be placed in hot air oven for dryness, to remove all the water molecule from the precipitates. After removing all the molecules of water from the precipitates, these precipitates will be weighed, and calculations will be made for the quantitative analysis of a targeted compound. Here in this slide, you will see the protocol to perform a gravimetric analysis. The first of all, you will have to prepare a solution by adding a considerable amount uh, of the solute into the solvent. So, what is the difference between an amount and the concentration? Amount is any weight quantity. However, the concentration is defined as the weight quantity of any solute dissolved in a particular volume of the solvent. So we should be very clear about these two terms, that amount and the concentration. I repeat, amount is an weight any weight quantity, कोई भी measure की हुई quantity is weight quantity. And then what is the concentration? Concentration uh, is is a unit to express the amount of the solute in a particular volume of the solvent. So this concentration can be defined as the amount of a solute dissolved in a specific volume of the solvent. So after preparing the solution, a large amount of the precipitating agent is added, which will be reacting to the analyte present in the solution. And when this reaction will be processed, as a result of the reaction, some solid particles will be formed. These solid particles will be known as precipitates, and this mixture And when these precipitating agent and the solvent are reacting together, this this reaction is allowed to incubate at a suitable at a required temperature, which is prerequisite for the completion of the gravimetric analysis. uh, After the reaction, some solid materials will be formed, which will be known as precipitates, and these insoluble precipitates will start forming after appropriate times. These times may vary from 0 second to from 0 minute to 24 minutes, 24 hours. So it depends upon the process and depends upon the precipitating agent and the solution analyte that you are going to mix. After the formation of the precipitates, these precipitates will be separated or isolated by the process of filtration. In this filtration process, we use a filter paper of specific properties. This filter paper, the use of filter paper depends upon the size of the precipitates. And after separation of these precipitates will be freed from the moisture. Usually when these precipitates are formed in a mother liquor, so as this mother liquor contains a lot of water, so these precipitates have plenty of water in their in their crystals. So in order to remove the water molecules from the precipitate crystals, these will be dried, these will be kept in hot air oven to remove the moisture. And the temperature of the hot air oven is very important, as if we if we are working on a higher temperature, then the higher temperature will burn the precipitates. And if we are choosing a lower temperature, then this lower temperature will take a lot of time to dry these precipitates. So in order to perform a comprehensive analysis of gravimetric analysis, we must be keen to select the relevant temperature, and this temperature depends upon the the conditions of the reactions. And after drying, these precipitates will be weighed. The weight quantity of the precipitates will be the basis of the calculation of the analyte, of the targeted analyte. In this slide, the process of filtration have been shown, and you can see you need the following apparatus for uh, the completion of filtration process. You will have to take this uh, well washed clean glassware. These glassware includes a beaker, a funnel, and a stand on which you can keep this funnel in upright position. So after formation of precipitates, a suitable filter paper will be chosen, and this filter paper will be folded using this picture. I mean, you can just fold in a twice section, then make it a four section of a filter paper. And using this filter paper, you can filter the reaction mixture. This reaction mixture contains actually precipitates and the mother liquor. So in order to separate the mother liquor and the precipitates, we'll use this filter paper and a funnel. So you will pour, you can see here in this image, when you pour your reaction mixture on the funnel containing a filter paper, this filter paper allows only the mother liquor molecules to pass from the filter paper and stop the precipitates. In this way, all the insoluble precipitates will be taken on the filter paper, and all the mother liquor will be passed from this filter paper, and after that these these precipitates on the filter paper will be taken and will be dried in a hot air oven. In order to prepare a solution, we must be familiar with some basic terms or basic conditions we used in gravimetric analysis. Number one, volume. It means how much volume we are interested to have for gravimetric analysis, and the concentration, that means specific amount of the solute in a specific volume, and these concentration are of various type. Number one, percentage concentration. In this slide we will learn about the percentage concentration. The percentage solutions are those solutions in which we have a total 100 parts of both solute and the solvent molecules. So these percentage solutions are of four types. Number one, percentage weight by volume solution, percentage volume by volume solution, and percentage volume by weight solution, and percentage weight by weight solution. So if you are interested to prepare 1% weight by volume solution, then you will take 1 gram of the solute, and you will put that 1 gram of solute in a volumetric flask of 100 ml, and after taking 1 gram of that solute, you will make up the volume up to 100 ml. In this way you will have a total 100 parts of the solution. That solution contains solute and the solvent. So in this way you can have a 1% weight by volume solution, and if you are interested to prepare 1% volume by volume solution, then you will take 1 ml of for example, if you are interested in 1% honey solution, then you will take 1 ml of honey, and you will make up the volume up to 100 ml using a volumetric flask or any volumetric glassware. So the third category is 1% volume by weight. So in this category you will take 1 ml of in this category the solute is a solvent in a liquid, and your solvent is solvent will also be in a liquid. So both are liquid, but the uh, the resultant quantity should be in grams, because when you are going to prepare 1% weight by volume, then you will take 1 ml of the solute, and then you will make the volume up to 100 grams. In this way you will be able to get 1% volume by weight solution. And the last type is weight by weight. Then you will have, if you are interested to prepare 1% weight by weight percent solution, then you will take 1 gram of the solute, and you will make up of the solution up to 100 gram by using an analytical balance. So these are the four percentage types. In the next slide we will discuss the remaining types of the concentration of the solution. This slide is actually the continuation of the previous one. In the last slide we discussed about the percentage solution. In percentage solution we are dealing with the parts of solute in 100 parts of solution. In this slide we will talk about molarity, normality, and molarity, which are different expressions of concentration of the solute in a solvent. So molarity is actually the number of moles of solute that were dissolved in 1 liter of the solution, 1 liter of the solvent. So this molarity tells us about the number of moles of solute in exactly 1 dm cube of the solution, and we need two pieces of information to calculate the molarity of a solute. Number one, the moles of the solute present in the solution, and number two, the volume of the solution that contains the solute. The next one is the normality. Normality is actually expressed as number of grams, number of gram equivalent of solute that will be dissolved in 1 dm cube of the solvent. In normal solution, we will be dealing with two kinds of information. Number one, the number of gram equivalents of the solute and the volume of the solution. And the third expression of the concentration is the molality. This molality actually the number of moles of solute dissolved in 1 kg of the solvent. So molality uh, actually tells us about the number of moles of solute dissolved in exactly 1 kilogram of the solvent. And to express this molar solution, we will be requiring two kinds of information. Number one, number of moles of the solute, and number two, the mass of the solvent in kg. The next expression of the concentration is the parts per million. Actually, parts per million is this non always denoted as ppm, and it's when you are when you take 1 milligram of a solute and dissolve in 1 liter of the solvent, then you will have a 1 ppm solution. In addition to the concentration of the solution, we will be very careful about the presence and the concentration of the impurities in the reaction mixture, in the solvents, and in the precipitating reagent. And the next very important factor for gravimetric analysis is the temperature, because temperature has a significant impact on the reactivity of the gravimetric analysis. And the last parameter is a pH. We will be very keen towards the environment of the reaction chamber, whether it is acidic environment or is basic. Next slide we will see what's impact of this acidity or the basicity of the environment on the gravimetric analysis. This slide actually shows the impact of the environment on the process of precipitation. Impact of environment means the acidity of the environment or the basicity of the environment. If the environment is basic, then what happens? And if the environment of the reaction chamber is acidic, then what will be observed in the case of precipitation? So when we are dealing with the calcium oxalate, it's insoluble in basic media, but this calcium oxalate is soluble in acidic media as oxalic acid. So you can see in this picture, the left one is in the basic media. In this basic media, this calcium oxalate is in the insoluble form, and in the right picture you can see this calcium oxalate is in the acidic media and as in the soluble form. So when you are processing the process of precipitation, when you are doing the gravimetric analysis, you should be very keen towards the environment of the reaction chamber. If its reaction chamber, whether it is acidic or basic, it should be according to the requirement, according to the protocol of the analysis. If it requires a basic medium, then you will have to provide the basic medium for the reaction processing. And if the reaction requirement is acidic environment, then you will have to provide the acidic environment to the reaction. Otherwise, the wrong interpretation of the results and the wrong results will be taken out from this analysis. So in order to get accurate results, we will have to follow, and we have to we have to be very keen to the protocol and the procedure of the reaction or the analysis.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of two or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
If you are interested in any analysis, then there must be some protocol, some criteria to carry out that analysis. So if you are interested in gravimetric analysis, to perform a gravimetric analysis, then you will have to look for certain protocol and criteria in order to undertake it. So in this slide you can see there are 4 criteria which are important for gravimetric analysis. Number 1 is the targeted analyte must completely react with precipitating agent to form insoluble residue. So if you are willing to perform a successful gravimetric analysis, and in the earlier slides we discussed a lot about the preparation of solution, then you should keep in mind that solution should be the solution should be clear. No particles can be seen by naked eye, and there is no colloidal solution. It means the analyte that you are going to analyze, that analyte, that targeted compound, must be completely ionized into the solution. And if that compound is available in the ionized form, then this ionized form of that compound will react precipitating agent completely to form a solid insoluble residue. So if the precipitating agent and the solvents are not intermixing, are not reacting completely, then the exact amount of the product cannot be achieved, which is theoretically possible. So the targeted analyte must completely react with the precipitating agent. That's why the precipitating agents are added in an excessive amount in order to grab all the available ions of the targeted analyte. So for example, if you are interested to carry out silver nitrate and the chloride anion solution, then that silver from the silver nitrate and from the sodium chloride, that chloride will react with silver and will form a silver chloride, and the silver chloride will appear as a white precipitate at the bottom of the uh, container. The second important condition is the resulting precipitate must be of non-composition. That theoretically you are designing a reaction, and then you after designing that reaction you are going to perform a gravimetric analysis. You must be familiar with the product composition. If you don't know about the composition of the product, you cannot aim for the exact calculation of that compound. And the third important criteria is the product must be pure. No impurities, no contamination should be there with the precipitates. That precipitate must be in the pure form, and that precipitate must be bigger in size and less in number. If they are less in number, they have a bigger size, they will have a less surface area, and the precipitate will be more durable in the mother liquor. And if the precipitate is large in number, then there will be the chances that their sizes will be the smaller, and when they will have a smaller size and they will have a large surface area, then there are chances that they can react with the mother liquor, and as the smaller particles have a greater reactivity. So the precipitate must be pure, and the precipitate must be in a less number but a bigger crystals of precipitate in the mother liquor. And the last criteria, which is very important, that these product that these precipitate must be filtered by using a filter paper, or you can use a spin machine, you can use centrifuge machine, you can use sedimentation. So for this isolation or the separation of this product of a product or these precipitate are of enough size that they cannot pass through the filter paper. They will stay on the filter paper, and only the mother liquor will pass from that filter paper. So by using this process of precipitation, the gravimetric analysis, silver chloride is produced in the industry by the simple reaction between silver nitrate and the solution of sodium chloride. When they react each other, the silver cation of the silver nitrate will react with the chloride anion of the sodium chloride. They will form a silver chloride solution, silver chloride precipitate, white precipitate. These white precipitate will be deposited, will be settled down on the bottom of the container. In this way, by using the gravimetric analysis, silver chloride is being produced in the industry. This slide presents you the relationship between the solubility and the solubility product. First of all, we should know about the solubility and the solubility product. Solubility is a chemical property of a solute to dissolve in a specific solvent. So solubility is a measured in terms of a maximum amount of the solute dissolved in a solvent at equilibrium, and the resulting solution is known as saturated solution. So when the solute is not dissolved in the solvent in up to the maximum limit, then the solution is unsaturated, and it means the solution has a lot of space in its crystals to dissolve a further amount of the solute. Then the third term, the first one is saturated when the solute is dissolved in a maximum amount in the solvent, and the second type of solution is unsaturated when the solution has more spaces to dissolve the further amount of the solute, and then the next third type is a supersaturated solution. When the saturated solution is warm up to higher temperature, and the available spaces in the solvent will be greater, and in that situation more solvent can be added and dissolve into that solvent. It means there are three types of solutions: saturated solutions, unsaturated solution, and supersaturated solution. And what is the solubility product? Solubility product actually is a mathematical product of the dissolved ion concentration raised to the power of their stoichiometric coefficients. So the solubility product is relevant to the sparingly soluble salt when it is dissolved in a solvent. Here in this slide you can see the solubility product of the silver chloride is that AgCl is equal to silver and chloride ion when it is dissolved, because silver chloride is a sparingly soluble salt, so it will dissociate into silver and chloride ion. When you want to calculate the solubility product, it will be Ksp is equal to silver ion concentration and chloride ion concentration, and in at equilibrium both, because it is equal biovalent, it is has equal concentration of silver and chloride, then solubility will be equal to Ag silver, a silver and chloride. So if you want to relate solubility and the solubility product, it can be denoted as S is the solubility and under root of the Ksp means solubility product. So in this table, in this slide, you can see the solubility is equal to 1 into 10 power 5 minus 5 molar solubility product of the silver chloride solution, silver chloride precipitate.